Hi, I'm Reid Prichard, and today I'm going to be talking about a unique optimization methodology we came up for high performance computing, as well as talking a little bit about the results we found when applying it to several computational fluid dynamics models. High performance computing is vital to computational research, and here at the Fluid Group, our research would grind to a halt without it. However, it can be extremely expensive, costing $10,000 to $100,000 for a single simulation, and taking months or even potentially years to finish. So when you're dealing with numbers this large, optimization is crucial. HPC users have two objectives. First, you want to minimize core hours, or you want cheaper results. And second, you want to minimize Earth hours, or you want faster results. To accomplish this, several variables can be controlled. First off, machine type. With cloud computing comes a great variety of machines where it's often difficult to see which will be the best for your application without doing testing. The same goes for machine count, which is another double-edged sword of cloud computing. There's great flexibility where you can choose as few or as many machines as you want, and a poor choice here can have dramatic effects on the efficiency of your simulation, so it's important to do testing to establish this as well. Finally, undersubscription is something that's not commonly discussed, but it's the number of cores left unused on each machine. You might be thinking if I paid for 120 cores per machine, it would be wasting money not to use them all. But we'll talk about later just how important it is to leave a few free and to dial that in to maximize your efficiency. A naive analysis method would take the benchmark data and just throw it up on a scatter plot you can see on the right. And this is how we started doing optimization because it's kind of the intuitive thing to do. But this isn't a great method because in multi-objective optimization, you're just dealing with so many factors where you have three variables and two objectives. And that's complicated by the fact that in this multi-objective optimization, there's no one best solution. So you'll have one option that's fastest, one that's cheapest, and any number of options in between that compromise the two. But any one of those could be the best depending on your current needs. So the data need to be in an easily understandable form so that you can continually reevaluate the data as your needs change. Maybe a deadline is coming up and you want to switch to a cluster that gets the job done faster without costing too much more. So just plotting it on the right, like you can see, doesn't really do a whole lot. I mean, we can see from the square markers that, okay, 3 nodes of machine beta is the fastest. It has the lowest benchmark duration, but there's not a whole lot other than that you can glean at a glance from this plot. The first step to a useful plotting method is normalization. First, normalized runtime indicates the amount of time required to compute 1 second of solution time. You can see there that it's pretty straightforward. It's just the benchmark duration divided by the amount of solution time that was computed in the course of that benchmark. Cost is a little less straightforward because hardware hourly cost alone does not indicate your total simulation cost. Total cost also depends on your simulation speed. So for example, if you switch to faster hardware that was more expensive, it might cost more per hour, but it also wouldn't need to run as long because it's faster. So normalized cost disentangles speed from cost by indicating the cost to compute 1 second of solution time, where it's the node cost per hour times the node count, which is your cluster hourly cost, times the normalized runtime, divided by 3600 to convert from seconds to hours. If you're optimizing on local hardware, you're not going to have a cost per hour per se, so that could be omitted, in which case this parameter would just represent almost the opportunity cost, because undoubtedly you have many projects that you want to run and a limited amount of cores, so there is still some cost to allocating more cores to one project. It's desirable to decrease both of these quantities. So if the normalized runtime decreases, you know for a fact the simulation will compute in less time and proportionally so. So if you have your normalized runtime, you'll get your results twice as fast. Similarly, if your normalized cost decreases, the simulation will cost less start to finish regardless of its speed. So if you have your normalized cost, you know it's going to cost half as much. Finally, we create the Prichard diagram by plotting normalized cost versus normalized runtime. This produces a Pareto front. If you're not familiar with a Pareto front is, any point along the front where the front is that solid teal line is an efficient solution. So this is a point that you might want to choose depending on your needs, but anything behind the front is objectively bad, and it's guaranteed that you'll have at least one point on the front that is both faster and cheaper. You can see here where there are clusters of points close together, and you might be wondering what that is. That's just from the undersubscription testing. So it moves the needle significantly on this log-log plot, but not as much as, for example, doubling the amount of cores you're using. Generally, what's happening here is node count is increasing from right to left, which makes sense, right? More nodes is generally going to be faster. And generally, node count is also increasing from bottom to top, because you'd also expect that more nodes generally is going to be more expensive. So this Prichard diagram enables easy hardware selection based on whatever your current needs are. So here we've got probably 50 data points, and instantly we've narrowed it down to just 3 options. So for example, if cost were the most important factor, we can just look and see, okay, what's the bottom point on the Pareto front? And it's 1 node of machine gamma with 117 cores per node. And then if your objectives change and you want the fastest option, just pick the leftmost point on the Pareto front, which is 3 of machine gamma with 116 cores per node. In addition to guiding your CFD runs, this can also play into the optimization process. So I'll often use this to look at trends on the Prichard diagram to figure out which benchmarks I want to run next to get a complete picture of performance across the board. So for example, we can see that machine beta is kind of sloping downward and to the right. So it might be worth doing a test with fewer nodes of machine beta to see if it crosses over into the Pareto front and becomes cheaper than machine gamma on the far right. Let's quickly take a look at the Prichard diagram applied to 3 different meshes of the same computational fluid dynamics model. So model 1A is a version of the model with 300,000 cells, model 1B has 2 million, and 1C has 20 million. We can see by looking at this, as we would expect, that as cells per core grows, scalability improves. So whereas for the model with the fewest cells, model 1A, the Pareto front is nearly a vertical line, which means that it takes a lot of additional cost, a lot of vertical movement, to get very little additional speed or horizontal movement. Whereas on the other end of the spectrum, model 1C, we see a horizontal line, where it takes very little additional cost in order to get a lot more speed. So this is because of greater scalability of these lower cells per core. We see 2 things really interesting on this plot. Where first off on model 1B, you can see that the topmost square marker is actually to the right of the one beneath it. And this is dubbed negative scalability, because if you think about it, this point is a lot more expensive than the one below it, but it's to the right, it's actually slower. So throwing more cores at the problem ultimately slowed it down, which just shows that you can't make assumptions like that, and you have to rely on this optimization testing to get effective HPC use. On the other hand, we see with model 1C that the 2 triangular markers on the right side are actually above the Pareto front. So by increasing to that 3rd marker from the right, we got super linear scaling. So imagine doubling your core count and getting 2.5 times the speed. This shows that on the other end of the spectrum, you can be wasting money by using too few cores, and again, optimization is vitally important. Let's take a closer look at undersubscription. So very little literature discusses how important it is, and we were unable to find anything showing on an applied level how important it is for CFD users to take advantage of this effect. Many CFD users, even those at prestigious institutions, have never even heard this term, but we found speed increases of over 5% for each mesh and each model at large node counts. You can see on the right here that for one of our models, which we dubbed 2A with a machine type beta, we saw nearly a 2 times speed up just by leaving 3 free cores per machine with using 8 nodes. So optimization involves trade-offs where more nodes, more cores is going to be more expensive and it'll get you more performance at a cost, but this is free performance where you're just taking better advantage of the machines you already have, which is why it's so important. With HPC, optimization is vitally important, and the Prichard diagram condenses all of these variables and objectives into a single plot to make the process easy. Its use has saved the Liberty School of Engineering roughly $50,000 to date. Looking forward with this research, we hope to use all of the data we've gathered to allow prediction of optimality without requiring all the benchmarking. Thank you for listening.